Morning again. My name is Andrei. I'm working for Yandex, and actually, I'm like not a real scientist. I'm an engineer, and I'm mostly working on Postgres, on open source Postgres, on behalf of enterprise. And today, I'd like to discuss a collaboration between scientific community, which started data management stuff, and open source communities who try to pick ideas from scientific community. A few words about me. I'm working on Postgres since 2016, so not really for a long time, like 8-9 years. I was doing research in database indexing for maybe 15 years or so. Currently, I'm maintainer of few open source projects, mostly for disaster recovery and connection pooling and Postgres sharding. Average age is 24 years, so we're kind of young, and I'm the only most of my team are former students, like recent students. So what was in the beginning of modern Postgres that we are developing? Obviously, there was a scientific paper, and as you may know, this was a scientific paper written by Michael Stonebreaker. The design of Postgres was published in 1986, and you might think that there was a code, a working system. No, there was nothing even remotely close to working systems. There was just a consideration how to do it at the database that will be on par of working systems from IBM and Oracle. Stonebreaker created Ingress before, but the beginning of Postgres was not a code, just ideas. And the next year, on 87, there was another paper about how to do a Postgres, now about storage system, and the groundbreaking idea, let's create a database without write-ahead login. Like it's doable, but looking forward to these days, we don't know how to do a really recoverable database without write-ahead login, but still the paper was published and there was no code still. It's just an idea, and 2 years of scientific research, we have papers, but we don't have a working system. And then there was finally DemoWare system published on ACM Sigmund conference. It was shown in 1988, and it was not like production-ready systems. It was just a system for benchmarks, for prototyping, and for discussing the code. And then there was a complete rewrite version 1 and complete rewrite version 2. Each new version was released next year, mostly for having publications. So for several years, Postgres was something to publish, something to make a scientific paper, and no real system behind Postgres. But real energy of students moved the code ahead, and that was not just completely new system created from scratch, but rather already evolving. Like version 2 was somewhat resemblant to version 1, besides containing many new subsystems. And version 3 landed with like rewriting most crucial systems. Finally, at version 4, scientific community decided that now science is over. Postgres 4.2 is the end of research of a Postgres, and now we should switch somewhere else. And that's where real database started. That was a point when open source community, mostly consistent from students, decided that it's time to do an industrial version of Postgres, which landed as Postgres 95 because they needed to attract attention from industry and stop making publications and do a real system that works. And these students actually removed many scientific advancements. For example, querying language PostgreSQL invented for Postgres was completely removed from Postgres. They replaced this with standard SQL. And the same goes with many systems that they could replace. They still were students. They didn't have a lot of workforce. But in next year, in 1986, the name Postgres 95 was somewhat outdated, and they renamed it to PostgreSQL as we write it now, or simply Postgres. So the main idea here is that the project had a clear line between science for the sake of searching of new ideas and industrial implementation without publishing anything. The group that was in charge of Postgres later didn't publish much, and they didn't achieve academic goals most of the time, but they had acknowledgement from open source communities. How our development process looks now. To these days, we don't use like GitHub flows or something like that. We mostly communicate via mailing lists. We send emails to each other. And if you want to start contributing to Postgres, the first thing that you do is subscribe to Postgres mailing list, mainly Postgres hackers. We call engineers working on Postgres hackers. That's kind of our legacy, but we like this word. I don't say that I'm Postgres contributor. I don't say that I'm Postgres engineer. I'm a Postgres hacker. But later, when you go on with working with community, you will have to subscribe real lists like Postgres bugs and Postgres announces. These lists are more serious, more user-oriented, where we have to show our community that like we are doing serious project, not just hacking around. We have application which we call CommitFest. The thing with mailing list is that mail threads are getting lost. If it's not bumped for a few weeks, you can forget about some new ideas that were discussed. In academic paper, you have a stable way to return again and again to ideas that were expressed in papers. But in mailing list, we don't have such mechanism. And to do so, our mechanism of retrospection is CommitFest. That's the place where we register mailing threads with new features that we want to see in our code base in next release. And second thing that you are doing when you want to start contributing to Postgres, you go to CommitFest application and skim through current threads. Sometimes they point to mailing threads that are forgotten for a year or two, but the community wants this feature, and community wants someone working on this. That's why we have this CommitFest. As you may see, most of features that we want are marked as needing review. So the third thing that you are doing when you are trying to contribute to Postgres is picking a CommitFest item and going to mailing list and reviewing some code there. Here is an example of my CommitFest item for covering indices that can include unindexed columns. You can see that I proposed the feature on 2018 in July, and after a year or two, it was committed to Postgres 12. Here you see someone who is in charge of reviewing and who's in charge of committing the patch. Any idea that you want to implement is starting with a message that you are sending to mailing list, where you can prototype a patch, but still it's about ideas, not about the code. If you have a good idea, someone will pick it up and implement a code version. But if you want to implement it yourself, sure, go ahead and attach a patch to the thread. We don't use pull requests or change requests or merge requests or other systems. To this date, we send a patch, but please don't send diffs, because patch, most important part of the patch is a commit message where you describe what actually had changed. What the reviewer will mostly look not to your message, but to commit message of the patch that you sent. And someone will pick your mailing thread, and currently in Postgres Hackers, it happens almost instantly. When I sent my first patch to Postgres Hackers in 2016, I've sent it in, set on a plane to Ekaterinburg, and when I arrived to Ekaterinburg, I already had a response from Tom and Heikki. They reviewed my idea. I didn't write a patch. I just sent my idea, and the community is very responsible in answering promptly to new community members. If the community sees that you are working for a big tech company that is paying you for being patient and working precisely and for a long time, probably community will not be so swift. But if you are enthusiast, the community feels responsible to making your way in the community easier. And that's an important part of our culture. Finally, to get anything into release, you have to convince a committer. That's the one who will be responsible in fixing bugs. And there will be bugs. Every simple patch contains a bug. It's absolutely inevitable. For example, in this spring, I had a patch which added iteration count to watch query. So when you select something, you can say watch this query, repeat it every second. And I added iteration count there. I had 2 reviewers, and after a month of exploitation, there was a bug found in simple loop, simple iteration counter. Any patch inevitably contains bugs, and committers are in charge of fixing these bugs. That's why finding a committer for your patch is most difficult problem in our work. And if you see that some patch is important for you, you can review it and help attracting attention of a committer, because attention of committer is most scarce our currency, our value. Currently, we have like 30 committers in Postgres project, and we cannot really scale here. For example, Linux kernel project have much more committers, but they are modular. They have committers for network stack, for file system, for scheduler, etc. In Postgres, every committer is in charge of everything, because our system is too tightly interconnected. We don't have actually a way to separate zones of responsibility. Every committer must know all the code base, or at least pretend to know. It's just too huge. But let's return back to scientific stuff. From time to time, Postgres is an object of scientific research. Today, mostly this happens when the industry is trying to solve some Postgres problem, and the biggest Postgres problem is, of course, scaling. Typically, some industrial paper looks like this. Some big company, in this case, it's Microsoft, is trying to make sharded Postgres. Postgres that is operating on many nodes, on many writing nodes. And typically they discuss TPCC or TPCH tests and see how it actually scales. And today, all these scientific papers have some limitations. In case of Citus, it's mostly analytical system, and like analytical system is scaled better when it's Postgres based than transactional systems. And another example of the same thing going from industry is GreenPlum-DB. GreenPlum is maybe 5 or 6 years older than Citus. All these scientific papers are heavily discussed in Postgres community because they are open source. You might know that there are forks of Postgres that are closed source, and we don't have incentive to look into these papers because even if it's important scientific ideas, we still feel that our value is open code. If it's not open, we don't have much interest in discussing these ideas. Typically, science from industry is about tackling limitations that were in proposed systems. For example, here is a GreenPlum paper where they try to improve their transactional workload. So they have analytical systems that is trying to be better in as transactional systems. Or previously Citus, which is better in actually doing transactional workload, trying to be better in analytics. So they move in somewhat one space dimension. Here's an example of similar Russian paper from Mikhail Zimbler and Konstantin Pan. They called their research PostgreSQL, and the idea was that they proposing client-based sharding for Postgres. I'm not sure if this idea went ahead and they had industrial implementation, but the idea is very interesting. I think it's inspired by Cassandra routing, which can be implemented in the driver on client side. But let's move on. Another way when Postgres is subject of scientific research is trying to replace Postgres in somewhere with something else, because Postgres is kind of a stable system that can be used anywhere, and many problems that are solved with Postgres are solved in suboptimal or maybe even wrong way. And there is a lot of scientific research that is trying to replace Postgres with something else. Usually it's papers that highlight our weak sides. And we as a community of Postgres should pay much attention to these papers and try to see why our system is, how our system can be improved. Here is another example, like finding a new type of data that can be operated with Postgres. It's MobilityDB, spatial temporal data. Quite interesting research, but this research was mostly backed by bless you. Mostly backed by existing technology like generalized indexing. Some histories from using scientific research, scientific papers in industrial implementation of Postgres. There was a great review article written by C. Mohan in beginning of 1990s. It was about using it was about systematizing the way write-ahead logged systems work. And Mohan reviewed many databases and decided how to do like how to integrate all the ideas from working industrial systems. And 8 years later, Vadim Mikheyev tried to read this paper and implement ideas of RES in Postgres. He started with just reviewing a scientific paper, worked hard for a year or so, and he ended up with like not using all the write-ahead logging, not using ideas from RES at all. Like RES tried to combine all the problems of typical write-ahead logging and solve them. The thing is, when Vadim Mikheyev was working on write-ahead logging, he implemented multi-version concurrency control without knowing that RES exists. That's why we have a separation of indexes and heap tables. The way we cannot implement real RES with undo log as it is done in a DB. Actual open source implementation had to started with trying ideas from RES, but ended without undo logs at all. We have a just typical redo log, and that's it. And now, 20 years later, we have a problem of this vacuuming and problem of like real undo logs. This decision that was made by engineer, decision to avoid scientific knowledge, after 20 years create some huge problems to community now. But well, the system is evolutioning with resources that are available at the moment. And back in October of 2000, that was the way to build a working system. Postgres was not popular at that moment. Postgres was a system to be developed yet, to be trusted yet. And that was a perfectly justified decision made by Vadim back then. Another story of serialized snapshot isolation. For many years, Postgres on repeatable read isolation pretended to be serializable, which it was not. But in 2009, there was a dissertation by C.J. Cahill in Australia that was proposing relatively fast technology to make repeatable read in Postgres, also serializable isolation level. The dissertation of Michael was discussed in Postgres hackers, and some hackers decided to try to implement it in an industrial way. And later they wrote another paper, which is called Serializable Snapshot Isolation in Postgres. It was in 2012, I think. Yeah, there's a number, 2012. The interesting part is that it took 3 years. Despite dissertation of Cahill was implemented in BerkeleyDB and implemented in InnoDB, InnoDB still do not have this technology. Resemblance of BerkeleyDB to Postgres convinced community to try to do this. And Kevin Gritner, as an engineer from Postgres community, decided to do implementation. He shipped a first version of serializable snapshot isolation in Postgres 9.1. But still, we are collecting some bugs. For example, in 2020, we had a report from Jepson. Jepson is a nickname. His real name is Kyle Kingsbury. That at some point, Postgres is accepting some schedulers are serializable that are not really serializable. So we were fixing bugs for 8 years when we took as is scientific idea implemented is seemed easy, but actual fixing stuff took many years. Recently, I had a survey in community who is using actually serializable level, and to this day, many engineers that are using Postgres still consider serializable isolation heavyweight and CPU intensive, and prefer to implement their systems upon read committed or repeatable read isolation levels. And finally, third history of scientific research that made its way into industrial database, which is closer to my research areas. It's generalized indexing search trees. Generalized indexing search trees, or simply GIST, started as usual. They started with a scientific paper by Joe Hellerstein and his friends. It was mostly the idea of generalized many access methods like R trees or R star trees or N trees or all the other trees. They wanted a simpler version of indexing for new databases. And the idea of some simplicity was welcomed by open source community, but still it was mostly idea that was hard to apply to real open source code. The next step happened again with researchers. Marcel Karnacker wrote his PhD thesis about doing GIST more concurrent. He described a way for crash recovery in GIST and described locking protocol for concurrency in trees. But still, this was not enough. The Postgres already got its name. It was not Postgres 95. It was not developed in university. It already had some enterprise behind it. But still, this idea was just an idea, and but with very systematic description of how to do it. Dissertation contained documentation that was somewhat enough to start working, start coding. Few engineers from Moscow, Oleg Bartunov and Theodor Sigaev, picked this idea. They were astronomers, and they started with implementing R3 for their needs. They needed astronomical database, and they implemented R3s, and they picked the dissertation by Marcel Karnacker and thought, okay, we can extend our astronomical stuff on other stuff. And this worked well because they were not really into scientific research. They wanted something working, something that can be of use to general engineer, to broad audience of engineers. So they created a first implementation of R3, then renamed it completely to generalized search trees, effectively solving problems that were not solved by scientific work of Marcel Karnacker. But you might think that this is the end. No, it was in 2005. Let's skip 10 years of development. I joined development of GIST in 2015, and every year we ship some fixes or some improvements or something that can be done better in GIST. GIST was currently is mostly used for maps. It started with R3, and currently it's popular because it supports R3. For example, maybe you used Yandex Taxi or Yandex Maps. They're backed by GIST in some way. They are backed by Postgres, which is backed by GIST. So fast forward to our days. currently, last supported version of Postgres is Postgres 11. It will support of Postgres 11 will end next year, so that's where I'm starting advancement of GIST that are still going on. In 2017, my student in Google Summer of Code project, Shubham Barai, combined serializable snapshot installation and GIST. Before that, if you accessed something via GIST, you had a predicate log on a whole table, so there was a lot of conflicts generated. It was relatively complex work, but Shubham didn't have any inclination to do it as a scientific work. So no papers were published, just a commit to master branch of Postgres, and that's it. Of course, with bugs, but I will not stop here. In Postgres 12, I've implemented covering indexes in GIST, allowing you to include some columns that cannot be indexed by that don't have operator classes of GIST. I developed it mostly because it was prescribed by new standard SQL 2015. In next year, it was committed by Alexander Korotkov. Like I told that I have implemented it, but I should say that we had done it together with Alexander. As usual, you can see that I've proposed it is 2018 and it was finished in 2019. It's relatively fast for patches in Postgres to be done in 1 year. Typically, every new thread is welcomed by Tom Lane, the guy who is in charge of approximately 1/3 of commits into Postgres. Still, he's working really a lot. And if you will have a review of your patch, most probably you will have a review of, by Tom Lane. Here, I'm not mentioning any fixes by Tom Lane because if I had bug in every single patch that I committed, and mostly they were fixed by Tom. So thanks to Tom. After 2 years of using this in production, Pavel Borisov found a bug in my patch of covering indexes. And that's it. So far, 3 years, we don't have bugs in these subsystems. That's one of stable subsystems that I've implemented. But still, there are some ideas where we can improve. And if you want ideas for new patches, you can address me and I will reply you with these ideas. In Postgres 13, I was working mostly on GIST vacuum. This is our technology that we have to have because we didn't implement ARIA as Mohan told us to do. So we have to vacuum our indexes, and GIST indexes were vacuumed by logical scan, which is slow on many devices. And I was surprised that it was slow even on solid-state drives. So we removed old logical vacuum with physical scanning of file. Now it works relatively better. We have some good feedback from a community. This is a transformational change. It allows geographical indexes to be more dynamic. So before having a physical scan vacuum, if you are inserting a taxi on a street in the indexing, you have to delete all the old pointers which leave bloat in the index. And having a physical scan of a GIST allowed us to remove this bloat cheaply. And before this technology, it was easy to index statical objects like buildings or streets or something that is not moving. But indexing of moving objects created just too much bloat and occupied too much space on the disk, and too much time was taken to remove old versions that we had to have because we didn't listen to Mohan. Okay, let's move on. Some other commits that we don't have time to discuss. As usual, we have someone in the community who is driving new features that they just wanted. And this is an example of like noise created by Dorofei Praliskovsky, who was a map engineer in Juno, also taxi company. And he was very upset with the performance of our spatial indexing. And first thing he did was to annoy Nikita Glukhov to port B3 index build to GIST. And Nikita did it, but in a scientific way. Like he did a prototype that is working 10 times faster than industrial implementation, but is not usable in production because the code was just proof of a concept. At this point, Dorofei, for some reason, decided to annoy me. Finally, he convinced me to port this code in an industrial version. So in Postgres 14, we had a sorting build, which is 10 times faster than usual GIST build. As usual, we had few bugs that we're fixing that are still in progress, like we find some bugs these days, but the system is exploited on millions of servers, so should be stable enough. Here is some benchmarks. So without sorting, we could create an index in 2 seconds, and with sorting we can create an index in 200 milliseconds. So as I said, it's almost 10 times faster. The index is smaller, but actual selects are 2 times slower. Because we created cheap index, it's working worse. That was somewhat expected, and I think we should publish this story of doing cheap index somewhere in scientific papers, but we simply don't have time to do so. We are doing something new because Dorofei is nagging me to make code better again. Some other stuff that was implemented, some bugs fixed by Melanie Plugiman. Finally, Oleg Bartunov, who was original author of GIST implementation, make a talk at PGCon that our indexing is bad. Well, what's bad? It was almost scientific way he did research about how our index is operating. He drew lines of time to make a nearest neighbor search on maps and showed us that typically our index is working just normally, but it's working badly exactly at same points where it's needed to work better. So we had like proof that our fast index is working okay on average, but in most interesting points where data is actually searched, it's working bad. So he convinced us with Sergei Shulbakov and Alexander Kolenik from Contour that we have to implement new version, which is creating slightly slower indexes, but they are working on par with performance of unsorted build. So we did it. Again, it could be scientific research. We did it in scientific way. We had a review of many papers. We had experiments showing that we had a hypothesis that we proved that our indexing is really statistically better. But still, it was never published and probably never will be published anywhere besides commits logs of Postgres. We have a big list of to do, but I will not discuss these ideas because it's time to say that, as you can see, open source software is made and maintained by people and for people. And probably we as a community should think about doing it more scientific way to to transfer information and experience back into academia and to paper authors, actually. A few words about research in machine learning and AI. Still, AI is not really good in Postgres community. For example, a few years ago, you might see the paper which is called The Case for Learned Indexes by Google employees and Tim Kraska. It was like very visible paper trying to solve typical database problem with machine learning. But when the idea was refined to be closer to real implementation, we observed that it's more likely to be very well-known interpolation search or Newton search than something machine learning. So when the scientific idea of machine learning in indexing was condensed to real life, it became purely statistics. It became nothing fancy, actually. It became something that is known for 200 years. Currently, piecewise geometric model, which is an ancestor, which is inheritor of learned indexes, is mostly not a machine learning technique, but rather somewhat like industrial technique, yet not implemented in Postgres. So if you have some energy, you can try from this part. Another interesting place where Postgres is object of scientific research is applying machine learning to tune database. And mostly the work is done by Andy Pavlo. And recently he had a conference talk where he told that why machine learning doesn't work for databases. This is a clickbait. This talk was about why machine learning actually works for databases, but actually Andy did not invent this clickbait. This is a copy of a talk made by Oracle Larry Ellison. Larry Ellison had a similar talk. What's wrong with relational, which actually was about why relational models are good. So to condense ideas from Andy Pavlo and tuning databases with machine learning is that currently DBA is someone that is highly paid. Typically, DBA is earning 5-figure salary across the world. And if you're trying to automate like taxi driver, you have to interact with the real world. But when you are automating DBA, you already have these digital interfaces. You already have a connected database. But it's a pure theory. In fact, scientific researchers encountered the problem that interacting database is also hard. And the real problem is not picking a machine learning model or machine learning algorithm to tune database, but real problem is isolating staging workload from production workload. The real problem is the difference of real workload and production workload, and that the production workload is in fact usually a mix of many workloads working with databases, not the single one. So AutoTuner project by Andy Pavlo, mostly scientific project, they pivoted and now they are not providing a tuning mechanism that in charge of database settings, but now they are creating a AI augmented technology that is showing health of a database. It's not actually driving the database, but it's suggesting some ideas to not super qualified DBA. And it's true that you can hire super expensive and super qualified DBA, or you can try to teach former student to be a DBA just using AI technology, and this might work. The only problem that they encountered, they are trying to teach these students with usage of large language models and GPT. And GPT is based on information from the internet. That's like an obvious decision. But the reality is that most of best practices and so many advices in internet, they are simply wrong. And the knowledge base which we use to teach large language models contains just too much noise to give advice to DBA. In fact, if you think about it, like using LLM to teach surgeon, you will never do that, because like let the surgeon learns its way, typical way in academia and library. You probably would avoid from using large language models to giving advices to, for example, parachute jumper. Let him learn with usual instructions. So that's a problem to solve, but not by a community of data management, but rather of natural language processing communities. I'd like to finish with a history from Richard Feynman. He was encountered by some guy who was using abacus to calculate. Like it was entertainment in a bar, where a guy showed that he can calculate numbers very fast using mechanical calculator, and he offered Feynman to compete, like try to add numbers. And the guy showed Feynman that he's adding numbers much faster. Feynman proposed, let's try to multiply numbers, and they were on par, multiply numbers with almost the same performance, and they moved on to square roots and further, and the more complex calculation actually was, the better human mind was at it. And in fact, research and using of new instruments in databases is the same problem. We have new instruments like machine learning, like large language models, like new hardware, but still, this is just augmentation of our creativity. And research have to be the same. Research is all about the creativity. It's all about new ideas and seeing all databases in a new way. It's not about seriousness, actually. It's about seeing stuff that can be done better. And we as an open source community will pick up your ideas and try to implement them in open source way. Thank you for listening. I will be happy to answer your questions.
Inspiring talk. I have a question. Partly covered it during your presentation, but still, you mentioned using machine learning for improving Postgres in performance, but what about using Postgres for ML tasks and tasks of data mining, knowledge discovery? How you compare the facilities provided by Postgres to, in broad sense, knowledge discovery as compared to the competitors, to the competitors of Postgres?
Yeah, that's an interesting. Yes, yeah. About nearest neighbor search, currently, we kind of did it wrong way in low dimensionality. And in Postgres for many years, for decades even, we had this KNN that is working in 10 dimensions. But the reality of AI today is that they need to search in higher dimensions, in hundreds of dimensions. And this year we answered this challenge that we simply ported HNSW method into PG vector extension. So we have the facility of approximate neighbor search for machine learning, but we are really late because this technology was proposed 6 years ago by Artem Babenko and his team. And only in 2023 we understood that we actually have to implement it in databases. And now we have a typical database problems in this technology. It have no write-ahead logging. So if you have it on primary server, you don't have on replicas this nearest neighbor search. It don't have concurrency. If you are writing something into HNSW method, you have to log all the readers because it's not concurrent. It was scientific prototypes that we now have to use in production. So we just realized the problem that what we as an industrial community were doing it wrong. Databases for machine learning are not implemented the best way in Postgres right now, but we are actively working on this, and probably in a few months or so we will provide some solution. For this. I doubt that we can change something in Postgres core with machine learning and AI right now, but we are providing this. Yeah, currently we are providing extensions like PLR or PL Python. So if you have implementation of your method in Python, you can just import in the database this Python stuff. But the problem with Postgres is it was always around operational data. It was around services like a mail or services like banking or services like they are really ancient. The first technology that was used to automate business was not a computer. It was like actually paper. So currently database technologies mostly resemble paper, but just very fast paper. And so I think we as a pod source community should look more into novel researches like what is necessary for AI. But personally, I don't have an idea where to start, what to do for consumers of database technology like ML engineers. We even have a professionals like ML ops, something that is doing operations with production from standpoint of machine learning. But they are still distant from DBAs. They are not operating with production load of DBAs. They are not tuning databases.
Okay, thank you.
Thank you for the question.